Right. Let me start by welcoming you all to the School of Physics. I'm saying that because I know that there are some people coming from outside, so you're very welcome here. And of course, I can see quite a few familiar faces. So in case you're coming from outside and we don't know who we are, so here's my name, Professor Mauro Ferreira. I'm the Director of Postgrad Teaching and Learning, meaning I look after the postgraduate students here in the school. And today I'm going to talk to you a little bit about postgraduate opportunities in the School of Physics. Okay, so let's get started. And I'm going to tell you, now that you're approaching the end of your degree, it's a question that you will be asked, actually quite a few times, in this final year. What are your plans for after you finish your degree? Okay, and my experience tells me that you'll have one of the three answers, right? First answer is, I don't know yet. There's actually a variation for that answer. That's when you scream and runs away. That's another very common alternative there. The second answer is, I'm ready to go into the job market and I'll be looking for some kind of job, possibly in the industry or something. And the third type of answer that you get is, I would love to do a postgraduate course, okay? So if you are of that type, you're at the right place, because that's what we're here to tell you a little bit about the postgraduate opportunities that we have on offer for you, okay? But of course, one thing that comes up straight away is, okay, how can I do that? What are the possibilities, funding-wise? What's the story? What can I do here? Well, just to say that there are mainly three approaches. One is you can fund yourself, right? And you can fund your PhD or your master's, and that's absolutely possible. And in fact, there's quite a few opportunities like that. Now, there's another one, which I'm going to mention, which is PI-funded projects. What do I mean by that? Principal PI stands for Principal Investigator. Here we have the academic staff. We are all principal investigators. We are potential supervisors, and we will have our own funding. And if so, we can actually hire a student, if you like, where we're going to provide you a stipend as well, pay for your fees, and that's a possibility. In fact, some of the projects that you see here today, some of them we have funding available for that. And then the third part would be the IRC scholarships. Okay, the IRC scholarships are personal scholarships where you as a student will apply for in conjunction with a supervisor. And that's what I'm going to talk a little bit about right now. Is that clear? So the important point here is that it's not too early to start thinking about postgraduate opportunities. I know that sounds like it's incredibly early because you have just started your fourth year, but time flies, and you'll see in a minute that the deadline for some of these applications are just around the corner, and that's why we're having these now, okay? Right, so in case you don't really know about the IRC scholarship, this is Government of Ireland, a postgraduate scholarship program. It runs every year. This year, to the best of my knowledge, has not changed dramatically from last year, but it offers scholarships for suitably qualified individuals to pursue research, either master's or PhD. The vast majority of PhD, I should add, in any discipline. Okay. So what that scholarship offers is a stipend of $16,000 per year, tax-free. It also pays your fees. In fact, the fees are not fully covered because the Trinity academic fees are higher than this. So what happens is the school will provide the balance, okay? And there's also some direct research expenses, consumables, etc., etc. It's important to mention that it's a highly competitive process, right? So, and the criteria, these are based on the following criteria. 40% of the applicants. In other words, you have to have a very good CV. You have to be a competitive applicant. But that is essential, but it's not, you need more than that. You need a very good project as well. So that's why it's important to have a good project, and you need to liaise with the supervisor, potential supervisor, who can assist you in putting a proposal, competitive proposal together. Is that clear? Right. So of course, and then, like I said, these are the criteria, but just to say that the cutoff tends to be around 87%, which goes to show how competitive this is, okay? And in terms of the track record, Trinity is doing remarkably well. The School of Physics in Trinity is doing remarkably well, because over the past 3 years, we got about 26 PhD studentships, with about 9 per year, right? It's not bad at all. And of course, if you want more information about this, you can find this. Just look up at research.ie, and you'll find all the details about it. Now, let me cut to the chase and be brutally honest here. If you're asking, do I stand a chance of getting that? Well, of course you do, but just to say that it's important to understand that in order to do that, you have to have a first class or upper second class degree, right? In reality, the last 26 awards that I can remember, they were all awarded to students with first degree. So that's really a requirement, even though the guidelines, they do say that second class is also possible, but in reality, students with the first are the ones who stand a better chance, okay? Okay, and the important point, the key dates, deadlines. So the call is open already, and the important point is the deadline. The deadline is 31st of October, which means it's just about a month from now. And that's why we're having this as early as now, which is the 3rd week of teaching term. Because we want you to start thinking about this, right? Because if you are interested in taking one of these, in sending an application to the IRC, you really need to, here's how to apply, of course, the details are here, but the first step is to identify a project and a supervisor. This is paramount. Without a supervisor and without a project, you don't stand a chance, right? So that's why we are organizing this. And so what we're going to do now is we're going to show you in the next hour a range of projects. Speakers will have here about 3 minutes, okay? And in 3 minutes, we'll have to showcase, right, some of the projects that are available, okay? Just to be clear, the idea here is not to give you a lot of detail about the project, just to give you a glimpse, a flavor of what the project is about, what the research field is about, and the idea then is for you to come and talk to us, right, to know more details about the project, about the area, and that's what we're going to do. Of course, the next hour we'll have these short presentations, and then after that we're going upstairs where there'll be, well, I'm not sure if I can call that a reception, but like, maybe some soft drinks upstairs, and then you have the time to talk to us about that. Is that okay? Now, I think we can start, but I'm going to start, and then just because now I'm talking to my colleagues here, because there are 17 people to speak, and I'm giving you 3 minutes each. You do the math. It's about 50 minutes, right? So what I'll do is I'll give you, each one of you, 3 minutes, right? And I'll put a timer here, and if the alarm goes off, you know what that means, right? And I will go first. Right, and I'll show you that I will press the start button.
I've got you now.
Right. Okay, so there we go. Start. Right. Okay. Let me tell you about what I have. My project's called Inverse Modeling Complex Media. Okay. Just to tell you, recently I've been working actually in conjunction with Shell, the oil company, where we developed a method that can map the subsurface of the Earth in a very efficient way. In case you don't know how that works, seismologists, what they do, they produce a small explosion here on the surface, right, and they measure this sound everywhere. And then after they measure this, they do a reverse engineering process, or in other words, an inverse modeling, where you actually can map the subsurface of the Earth, right? It's a very clever thing. Why would you want to do that? Because drilling is incredibly expensive, so you want to be sure what's down there, right? Now, am I telling you, am I advertising this for you to work for Shell or something, or as in seismology? Not exactly, but just to say, we have developed a method that maps the subsurface at a fraction of the time taken by standard methods. So what does that have to do with this project? Well, in fact, we can take this idea outside of seismology and bring this to the nanoscale, for example. Can we use the same ideas and try to map not the subsurface of the Earth, but maybe a very, very complex media, such as a pile of 2D sheets stacked in a disordered way like this? In principle, we can. How? You have to come and talk to me, and I'll tell you the details. That will be project number one. Project number two is that, of course, if that works in the nanoscale, well, the question is, can you do this with other waves in addition to acoustic waves? It turns out that you can. For example, using electromagnetic waves, you can do that and play around with ways of improving telecommunications. In fact, this project is done in conjunction with Connect, which is the research center just around the corner, dealing with telecommunications. And these are the two projects that I have available. It's worth mentioning that funding is currently available, in addition to a few other projects that we have here. So if you are interested in some of these projects, or if you want to know a little bit more about other projects, please come and talk to me. What I want from you is this. If you have a solid background in quantum mechanics and condensed matter theory, you're the right person for the job. If you like challenging problems, you're the right person for the job. And if you like interdisciplinary fields where you can apply physics to a whole range of other sectors, other fields, you're the right person for the job. 10 seconds to spare. I'm proud of myself. Good. Oh, by the way, let's not waste time with clapping, right? Because we have like 17 people to speak. So the next one is David. You cannot hear that sound.
Where are the projects? They're all over there.
Louise, you're next, okay?
Okay, so Dave McCluskey is my name. So I would have taught you, maybe you might remember me from second year a long time ago, if you did your undergraduate here. So my research is in the area of what we call nanothermal research. We have a small group which normally has a few postdocs and a few PhDs. As you can see, we're not very good with gender balance right now, so we're looking to address this. If you can help us with that, we'd be very happy. So what is nanothermal research? So we look at different ways of mapping temperature at very fast times and very small scales, and also not just temperature, but how energy moves from one place to another in terms of phonons and electrons and heat flow. So if you remember, temperature is the average kinetic and potential energy of something. So here's a little molecule jiggling away at room temperature, moving around. So we want to kind of measure that, and then if we put this molecule in contact with something else, we want to measure how quickly that energy gets distributed, right? So we collaborate a lot. We've developed a number of techniques which work down to about half a micron in spatial resolution and about picoseconds in temporal resolution. And so we work a lot with companies like Nokia, Analog Devices, Western Digital to approach some of the problems they're having at this size scale. And we also collaborate internationally with sort of Barcelona, Marseille, and Denmark and places like this. Okay, so an example of a project that's going on right now is looking at heat transport from solids to liquid interfaces, right? So solids are these very tightly bound things that like to vibrate at quite high frequencies. Liquids can rotate around, they have additional degrees of freedom. So you can imagine trying to get vibration across from the solid to the liquid is a problem. And then you can add in things like phase transitions into gases. So here we have video of something that we're studying, which is we have a laser coming in the back of a thin gold film. It generates a bubble in a liquid, and this is an evaporation or phase change process. And then there's these little droplets in here are actually condensing liquid. So the bubble forms, condenses, and comes back in. And this is in conjunction with Nokia. And the idea here is that we want to use this two-phase process. So we want to put this on top of a laser and on top of an integrated microelectronic device to cool down on a microscale. And phase change takes away a lot of heat, right? You've got your specific heat or your latent heat of vaporization. And so this is a really quick way to cool things. Second project that we have in the pipeline that we'd like some extra support with is called daytime radiative cooling. So this is where you optically design a surface such that it's very reflective in the visible, but in the mid-infrared it's very absorptive, which means it emits a lot in the mid-infrared. And what you can do here is if you design this in the atmospheric transparency windows of the atmosphere, you can allow the material to interact with space, which is at 3 Kelvin. And so this, just by doing this, it starts to cool down. So it will cool down about 10 degrees below ambient. And so you can imagine this can be used for a passive air conditioning system. And this is in collaboration with the mechanical engineering department who do the heat transfer. And we also have input from Concern Worldwide who are interested in applying this in developing countries, both in urban areas and in rural off-grid kind of areas. Okay, so I'm at 3:04. Am I done?
11 seconds left.
Okay, so yeah, if you have any further questions, you can email me. I lost it now. I was doing so well. So you can email me at mcc@oskd@tcd, and I'll hang around to answer any questions.
Thank you. Yeah, I'm watching there.
Yep.
Stefan, you're next, okay?
Okay, so I'll keep this really brief. Basically, my group works on nanophotonics and plasmonics. So we work out nanoscale structures and the light interaction on the nanoscale. We're working with dielectrics and metals. So we have a currently funded PhD position to start in September 2020. What that project is specifically about is developing nanoscale metallic structures which will give very high light concentration on a very, very small dimensions. So the application areas for this are, for example, to look at heat-assisted magnetic recording, and we want to be able to look at materials which normally don't melt. So some of the problems, for example, are if you use standard gold or silver, that at very high temperatures they start to melt, and that's what happens if you condense electromagnetic radiation down into really, really small dimensions. It starts to heat. So we're looking for what are known as optically refractory materials, which basically can withstand the high temperatures for the very high light concentration that we want to achieve. So this is also useful for solar cells. So they're the kind of two application areas. So for example, here's a gold metallic structure sitting on top of a silver disc with a spacer in between, and you can see we're able to get very high light concentration underneath the gold metallic structure. So we want now to be able to bring this to different geometries and in different kinds of materials and dimensions. So the kind of things that you need to be interested in, or the kind of skills that we want from people, we want people who are interested in learning about materials deposition. So we want to create new materials which will be able to withstand these high temperatures and still have the plasmonic properties. We're interested in the design of the structures that we want to use. So we'll be using numerical simulation techniques such as finite difference time domain and finite element modeling. We'll be doing our own structures which we fabricate using E-beam lithography or focused ion beam etching, and then we have to characterize the structures. So we look at single nano antennas, super lattices, and array type structures, and we use a range of commercial optical characterization tools as well as our own custom built systems. So there would be a part of the project which will be designing your own system. So that's currently funded research, but on top of that we also have a lot of other research areas within the group, dynamic plasmonic systems, dielectric nanophotonics, strong coupling on the nanoscale, and if anyone is interested in one of those, you can come and talk to me, and there's the possibility to apply for IRC funding in those areas instead. That's it.
Excellent.
I won't be around later, so if you do want to contact me, it's at louise.bradley@tcd.ie. And just to say, finally, that if you have a first in third year, that is sufficient to apply for the IRC.
Thank you.
Yes, because there are students who, if you look like you're going to get a first overall, you can get the funding, and if you only get a 2-1 for some reason, if you've been unlucky one of the exams, you will still be allowed to draw down the funding. So it's your trajectory that counts, not your final.
Thank you, Louise. You should have given the introductory talk yourself. It's much better. Thank you.
Thank you, Maro. Sorry, I can't stay.
Thanks.
Just to comment on the first, I'd like to underline that from my own experience that students who applied who didn't have first were really struggling to get these grants. So I would like to have students who were the first to apply for that. Important though is since everybody who light so good is that you have something in your CV that sticks out. Maybe you did a good summer project. Maybe you even managed to get a publication. Maybe you worked abroad or something like that. Something that looks special.
You know, I'm counting your time.
I know that. No, that's not fair.
Just note
that doesn't count.
There are other schemes that you can apply to. If you haven't got a person earlier, just this IRC is quite specific. So as Louise said, she has some funded projects, and Mauro has some as well. So don't be worried, but just a specific one.
Okay, I'm Stefan Hutzler. My research expertise are foams, bubbles, the stuff that you see in a pint of Guinness or in a cappuccino. And I'm also interested in how these bubbles pack together. And so I do also work on general properties of the packing of objects, simple objects. One picture is over there that we made a couple of years ago that looks like atoms, but they're actually soap bubbles where Mauro is. Stay where you are. We see that foams are an example system of a model system for deformable bubbles, for soft matter. And being that, we often thought it's an example that we should also have a relevance in biology. And I've shown you a few pictures here. This is a photograph of soap bubbles coming out of a tube, which crystallize in a certain way, self-organized. That's a computer simulation. We do lots of computer simulations in my group. And these are photographs of similar structures that this was taken in Bushy Park by one of my students. Over there, again, photograph of soap bubble that arranges in a certain way. This is a simulation of this. And this picture is the so-called the organization of the vacuolated cells in the zebrafish notochord. So it's an example from biology. It's sort of the backbone of that fish. But the structure is the same, and I'm not going to tell you exactly the details that you find in there, but it's found in biology also, what we do. And the aim of this project is to explore that with our simple experimental experiments that we do and simple simulations to reach out to these biologists. What we've done here is, this was something people by the Common Books last year called the scutoid. It was advertised being a new geometry published in Nature that people found fancy simulations in the so-called epithelial cells, curved cells. And when we looked at that, we said, well, that's nothing fancy. We can do this with our soap bubbles. So we got into the lab, and it took us 2 or 3 days, and then we made these scutoids in the lab with bubbles, and we were able to simulate them. This was a big group with about 20 authors, and we made it into a Nature paper. We were only a small group with 3 people, and we made it into a philosophical magazine. Impact factor difference 20 or something like that. In any case, so I now, in this project, when we talked to a couple of bioengineers as well, who are interested in bringing some of the information that we have about these structures and making that connection stronger between organization of biological cells and bubbles. It's minimization principles that are at the forefront there, packing as dense as possible on the lowest surface area. Thank you.
Charles, you're next.
Okay, so my work is in modeling condensed matter and molecules, and particularly the interaction between light and matter. So the things that I'm interested in are many body effects and the light-matter interaction. I'll say a bit more about that on the next slide. In the past, we've done a lot of work on semiconductor surfaces, in particular reflectance, and being able to probe what's happening to electrons in the very last couple of atomic layers at the surface using reflectance of visible light. A new area is in organic LEDs. There's a big push now, if you think about John Coleman's group and similar groups to that, in developing organic LEDs. Conventional LEDs contain things like gallium arsenide and so on, nasty inorganic things that may damage the environment. Organic LEDs are not nearly so bad for the environment as existing ones. And TADF OLEDs are thermally activated delayed fluorescence. Okay, this is a way of greatly increasing their efficiency. Last week, I was at a meeting where almost the entire topic, or the topic discussed during the whole week, was the beta-salpeter equation. You'll see that on the next slide. And besides just running codes, I do a lot of work with code development. So there'll be C language, message passing interface, and OpenMPI, ways of parallelizing your code, and using a lot of linear algebra, numerical analysis techniques to handle large amounts of data. The many-body techniques that are used these days produce really good agreement with experiment. This is a large bacterial chlorophyll molecule, and the solid line is the absorption spectrum of that molecule in solution, and the red is the calculation. These are some of these OLED molecules. These are the kinds of things that are in high-end TV screens these days and in your smartphone display. Okay, many body effects. This is something called the polarization propagator. The equation is the beta-salpeter equation. If you stick with this approximation, the usual picture that you're taught as an undergraduate of electrons going between levels applies, but all the stuff that changes that dramatically is in this kernel K star, which contains these Feynman diagrams. So if you're interested in the quantum mechanics of many particle systems, Green's functions, Feynman diagrams, come and talk to me. Charles.Patterson at tcd.ie.
Thanks, Charles.
Okay, so my name is Cormac McGuinness, and my expertise is in the electronic structure and investigating the electronic structure using X-ray spectroscopy. So in particular, I'm interested in looking at one-dimensional assembled nanostructures. So if you come to work with me, you'll be combining material science, surface science, self-assembled nanostructures, optics, and electronic structure. And in particular, for the project that I'm developing at the moment, is we're taking something like a porphyrin molecule, which Charles mentioned a moment ago, which is at the center of the chlorophyll molecule. And with different metals involved, we have different chemical functionality of these. And we can introduce this on the surface and assemble it into a graphene nanoribbon. So this is an STM of a porphyrin functionalized graphene nanoribbon measured by STM, where in principle, if we start to take this off the growth surface and put it onto a device-capable surface, then we can use it as a field effect transistor, and then in principle, we can also then use it as a single molecule sensor. If it works as a single molecule sensor, then we can do breath assays, we can diagnose from nitrites, for instance, are a significant signified lung irritation such as asthma, but also other things have been proven in terms of volatile organic compounds, have been proven to diagnose cancer. Not just simply lung cancer, but stomach cancer as well. So this would be the ultimate goal for this. So this is an on-surface synthesis involving molecules, incorporating porphyrins, looking at these via STM, aligning these, and then looking at these with X-ray photoemission spectroscopy, trying to transfer onto a device to create the sensor. Then ultimately we'll have a device then which interacts with oxygen or other volatile organic compounds that we can then measure. So the measure of the response of these nanostructures is what is important for us to do in the coming years. But in addition to those organic one-dimensional nanostructures, I'm interested in inorganic one-dimensional nanostructures, such as these iron nanowires on a platinum surface, which are covered with a gold capping layer. And the magnetic properties of these iron nanowires are very sensitive to the widths of the nanowires, the separations of the between adjacent nanowires, and the thickness of the capping layer and material which caps the layer above it. And so this will involve a whole variety of experiments both in Dublin, but also at synchrotron facilities such as Bessie in Berlin, to which I'm traveling next week for an experiment where we measure the magnetic response of this on an element-by-element basis using the variable X-ray wavelengths available at a synchrotron source. If any of this is of interest to you, then please come to talk to me, but I won't be able to stay very long this evening, so I'll leave one or two posters on the walls upstairs. Okay, thank you very much. If you have a passport, that's what you need for these experiments.
That's it. You're off to Kate, okay?
Okay. Hi everyone. My name is Kate Maguire. I haven't met too many of you yet. I only started as an assistant professor here back in March. And so I'm an astrophysicist. I look at explosions in the universe. It's something that I'm particularly interested in, the explosions of stars and then also the collisions of stars as well. So just to give you a flavour of my research, I'll give you two examples of the kind of projects that could be applied for students. So one of the things I'm interested in is the explosion of small dense stars called white dwarfs. So these are essential for measuring distances in the universe, and they're very useful in the discovery of the accelerating universe, and also the idea that there must be something acting against gravity in the universe, this thing we call dark energy. And so really what the aim of a lot of the work that I do is to try and understand how these actually explode. And understanding this correctly is really important for making future measurements of the dark energy and the cosmological parameters. Something more recently that I've become involved in is gravitational wave counterparts. So in 2017, the LIGO Virgo experiment discovered Einstein's prediction of gravitational waves from the merger of two neutron stars. But the key thing that I was really interested in here, and a lot of people around the world were interested in, we also saw the light from this explosion. So we actually saw the collision of the two neutron stars and the light that this produced. And this is also probably one of the ways where we get gold and platinum and the R process elements in the universe that are produced in this. And so this is understanding how this really happens is one of the key research areas I'm interested in. So how do we go about doing this? I'm an observational astronomer. So we use search telescopes in very nice locations around the world. So you'd have the opportunity to go to visit these telescopes and work with these telescopes. Some of these are in Chile and some are in the Canary Islands. Then we combine the search telescope data. So when we find a new target, a new transient, we need to understand more about it. And we find we take lots of multi-wavelength coverage. So from high energies, from X-rays, we use space satellites, and then we take longer wavelength observations on Earth. Then when we have these observations, we want to try and understand in a bit more detail, and so I work with collaborators across Europe and the world to try and understand what is actually going on. So if you want to try and understand the elements that you can see that are present in a spectrum, you want to do some kind of radiative transfer modeling to try and understand that better. And so this is one of the things that students could work on. And then finally, what are the kind of key questions that we want to answer? So what are the cell systems that produce type 1a supernovae? How do they explode? And how can we improve measurements of them for dark energy? And then also, is all the gold made in neutron star collisions? So far, we've found one neutron star merger. And so we want to understand, can you have neutron star black hole mergers? Do they produce something similar? And so there are many projects in this area that I'd be happy to discuss with anyone who is interested. Thank you.
Thank you.
Hi, I'm Stephen Carr, and I've just moved to Trinity with funding from the IRC. We'll talk about a little bit what we'll be doing in my group, which looks at quantum transport in two-dimensional systems. So what we do is a theoretical group, so we use theoretical and computational methods to study two-dimensional materials such as graphene and heterostructures that are made from different materials stacked or put together in layers in different ways. So as well as electronic properties, we're interested in more exotic properties related to the magnetic moments of electrons and other degrees of freedom with fancy names like Valley or pseudospin that arise when you put electrons into a two-dimensional lattice. So we have two main motivations. The first one is to predict new systems that allow us to manipulate these properties. so that they can be detected in future experiments and form the basis for future devices. Our second motivation is to simulate realistic experimental conditions where such systems are currently being measured. So to move away from the very, very perfect system where we have a single incoming electron wave, and to consider experimental devices where it's a messy system with defects and a lot of different contacts, and to see if the signals that are measured actually represent the underlying fundamental physics. So the methods we use span a wide range. We start analytics that can be done in pen and paper using the Dirac model for 2D materials, and we scale all the way up to quantum transport simulations containing millions of atoms that accurately represent the actual experimental length scale that these things are measured at. We also want to move into using machine learning and genetic algorithm techniques to aid in the design of this type of structures. So two possible projects that I would look for people to apply to the IRC with. The first one involves what happens when you have two layers of graphene stacked on top of each other and give them a twist. This was a very esoteric topic until recently, and this summer there have been 3 or 4 Nature and Science papers showing that this can be done in a controlled manner and at a range of unexpected and interesting phenomena, including perhaps superconductivity arise. But there's still a lot of open questions. What happens if this system isn't perfect? What happens if we add additional electric or magnetic fields? How can we interplay with this? Or if we couple the system to an additional layer, can we control it further? Another possible project is to look at the effect of strain. So strain, when you stretch something, you might be aware of in usual materials, but in two-dimensional materials, an unusual effect happens where the electrons act as if they're experiencing colossal effective magnetic fields of the orders of hundreds of Tesla, so far greater than can be achieved in a lab. With real magnetic fields of different signs, this can be used to control electron flow using these so-called snake states. So instead of the Lorentz effect where electrons move in circles, you can direct them along a path by changing the sign of the magnetic field. We want to see can we cause something similar by carefully designing a patterned strain so that the underlying pseudomagnetic field can induce a similar effect. So if you're interested in this type of project or something similar with two-dimensional materials using theoretical or computational methods, I'll be upstairs, and my office is in the Lloyd building if you want to come and talk to me about it. Thank you.
Here's the next. Stephen, is Stephen here?
Yeah.
Okay, he's not.
Yeah. All right, so my name is Matthias Möbius. My research area is experimental soft matter physics. In particular, I'm interested in the flow properties of viscoelastic fluids, basically gooey stuff, yes, and like foams, emulsions. But more recently, I got interested in nanosuspensions or nanosheet suspensions. So example, of course, are graphene. Everybody knows that. But there are actually many, many more. There's actually clays, yeah, like lapinite, for example, or layered materials like molybdenum disulfide, and so on. And we have techniques now to make these in large quantities. Yeah? And people are interested in applications of these. For example, you can make suspensions and make films that are conducting or semiconducting. You can put them into a polymer to make composites to enhance the mechanical properties. Yeah? The question is, do we understand the mechanical properties of these composites or of these suspensions? And the answer is not really. Yeah? And what does it depend on? And obviously you want to be able to tune that, right? So if you look at, for example, these suspensions here, yeah, at some point at a critical concentration they form a gel, yeah, so that's a network of particles, yeah, and then this gel is viscoelastic, so it will not just flow, it will also have elastic properties, yeah, so it will become gooey, yeah, and if you measure this for different nanosheet gels, yeah, you see this, yeah, so the shear modulus, yeah, so basically tells you how stiff that is, yeah, increases with the concentration, and they all seem to increase in the same fashion, yeah. So how, what does this depend on? Well, I mean, you can imagine you have this sheet of flakes, yeah, And if you now shear it or compress it, then that will depend on the mechanical properties of the single flakes and its size and thickness and so on. And recently we developed a model that seems to agree with the data we have, but this is just the start of it. So there are certain predictions that we haven't tested yet, and so we'd like to do this. And actually you can also use this experiment to say something about the mechanical properties of single sheets, which is nice. And also we haven't really explored much when you put this into polymers. I mean, the current models for polymer composites are based on engineering models which assume fibers that don't touch, which is obviously not the case here. But that's the state of the art at the moment, and we think we can do better. And so currently I have a fully funded experimental position on that topic, but there's also maybe possibility to do some simulations on that as well. Okay, thank you.
Stephen, you're next.
How long do I have?
David, 3 minutes. David, you're next, okay?
Is there a pointer?
Can give you one.
I feel like we're auditioning. It's like one of those talent shows. My name is Stephen Dooley. So my research team here focuses on low carbon energy. There is a pointer. Great. So we see this work as being very important. A typical project in our lab, multifaceted. So what we're working on right now is the proposition given by this diagram. Can we take renewable electricity and turn it into usable transportation fuels that have much lower net CO2 equivalent greenhouse gas emissions than the incumbent? So we work on this. It's a combination of physics, chemistry, engineering, and then also, thank you, technical economic analysis. So we need all 4 of those skills to be able to deploy this technology into the economy, and also to be able to educate policymakers to manipulate the economy to make the technology economically viable. So we know that we can't compete in terms of fuels with things that come out of the ground. So we have two methods, or 2 objectives. We have to really have a high control of the physics and chemistry involved, and then we also have to have reliable understandings of what the greenhouse gas intensity of those processes are, and also the techno-economics, so that we can argue for subsidies. So in this aspect, there are various projects here in terms of the deep physics of a solvated electron that would be used for electrocatalysis of CO2 up to CO, and then on to methanol. We then take that methanol, we perform acid hydrolysis of that to combine it with renewable carbon from biomass, to design fuels that are totally compatible with existing infrastructure and can be used right away, immediately, in the 1 to 10 year time frame that is needed from the IPCC to resolve the climate crisis. So our work is sponsored by a number of organizations, international organizations such as the International Energy Agency, the United Nations. We have commercialization awards from SEAI and SFI, and we also work closely with industry. It's very important because these are the people in the end that have to deploy the technology into the market. So there are a number of projects here, I'm going to run out of time, across that technology platform. You can read about them. They range from very deep, pure science of the physics and chemistry involved. We use a lot of modeling in my group. We try to pair modeling with experiment to really understand and prove things. So we're using a lot of numerical techniques, also density functional theory. A particular one right now is using chemical physics modeling to understand what the net life cycle greenhouse gas analysis is of so-called sustainable energy technologies. That really comes down to chemistry and physics, and those are things that we can quantify. So we're working on that. We want to work on it more. And also data science techniques. There's a lot of data being produced of the performance of all of these technologies. Too much data and uncertainties to analyze, really. So we need to take data science, numerical analysis procedures to better inform us there. You can read about the projects in contact.
Oh, you want to no, so you are to David, okay? David.
Okay.
point over? Yeah, you did good. Where are you here? I don't see there. Maybe you need to go back to the directory. Where's the directory? Here? Yeah, different formats.
You sent PDF to me.
Partly so. Hi everybody, my name is David O'Regan. I'm an electronic structure theorist who likes to develop new and improved theories and methodologies for simulating diverse systems. The work takes us from systems like oxides, so catalysis, light harvesting, and transparent display technologies to single photon emitting semiconductors for quantum information and biosystems. So my group and I develop a new theory, okay, new quantum mechanical theory. So if you like quantum mechanics, you like calculus and linear algebra, this could be a good project for you. We like to implement that in high-performance code that is modern, parallelized Fortran, also using graphics cards, and typically we work in collaboration, in big collaborations. So if you like to maybe get involved in a European project that maybe takes you on secondment, someplace like Cambridge for a month, that might be a good idea. And if you like the idea of using big supercomputers to simulate new materials, it could be a good project for you. Okay, more specifically, we're a well-respected group in developing new approximations in density functional theory. So density functional theory is probably the biggest thing that undergraduates never hear about in their physics and chemistry. And it's been reported in Nature that if you take the top 100 cited articles in any discipline that human beings think about, from Hittite law up to terraforming, from the year 1900 to 2014, 12 out of the top 100 pertain to the basics of density functional theory. So it's an extremely impactful area, and where we're focusing at the moment is improving the approximations used, in particular when looking at energy storage materials, such as battery materials. There's interesting quantum entanglement and other many-body effects that occur routinely in the batteries that occur in your phone or in your parents' electric car. And the state-of-the-art in quantum mechanical simulation cannot accurately predict even the basic crystal structure of these materials, let alone make predictions on the next generation of battery materials. But we believe that we have a solution to that in hand. So if you're interested in any of those topics, please come and talk to me. Thank you. Full screen.
Slideshow. Super. Super. Thank you, David. How do I do that? Right, okay. So I'm Paul Eastham, and I do theory of quantum light and matter. And I guess the question is why you might want to join my group. We're slightly bigger than this now, but not much. We're quite a small group. So one of the reasons you might want to do it is you want to work in a small group where you can work quite closely with me, maybe with some other students in the group. Okay. The other reason is if you want to do theoretical physics, and I might just say I don't consider that an activity just for the theoretical physics students. I have a physics degree, and you can do a theoretical physics PhD either way, and I think that's probably the case for many of the other disciplines here. Your degree doesn't tie you too tightly to a particular corner of physics. And what's the main qualification? I think it's the qualification for being a theorist, which is, do you want to make theories? That's what we do. And in my case, those theories are mostly equations that you study pencil and paper and maybe do a little bit of computational work on. So if that sort of activity appeals to you, and making theories of your own, then that's, maybe you want to work with us. These are theories about quantum mechanics and the fundamental behaviour of light and matter, particularly in small structures and materials, which all sounds very abstract and very far removed from reality, but it's not. we work quite closely with experimentalists, particularly to think our theories get tested in the lab. It's quite hard usually to persuade an experimentalist to do something just because some theorist dreamed it up, but we can do it and we do it. So if you're interested in doing theoretical physics, which has a contact with experiment and working with seeing this turned into something real in the lab, then we're the place also to talk to. And as I said, we're a small group and we work with lots of international collaborators. So I've got a bit about what we do here. Really, we're interested in the quantum physics of light and matter, photons and electrons, particularly in artificial materials and nanostructures. And the cool stuff is that's already quite weird and hard to understand. And then if you modify these structures, you can change these properties and you can make all sorts of interesting things happen. So some things we've discovered. One thing which we've shown here is that actually you can have funny properties for the angular momentum of light. And in some sense, you can have a photon which has a hot angular momentum of h bar over 2. Another one we discovered is that under some circumstances, quantum superpositions, like Schrödinger's cat being both alive and dead, normally that's a very fragile thing, and if you make something hotter, it becomes even more fragile. But we discovered that under some circumstances, actually, if you make things hotter, this is better for preserving quantum superpositions. And that's an interesting phenomenon, and it's also something you might think about for developing quantum technologies. And there's a picture over here, which is something we've worked on quite a lot. This is a Bose-Einstein condensate. So there's all sorts of things we're interested in students wanting to figure out. There's some ideas there. There's lots of other things you might be interested in. If you want to know more, give me a shout.
Bottom here, if you go to the bottom.
We ordered.
Yeah.
Hello, my name's Brian Espy. I'm an astrophysicist, but also with an interest in the environment. And if you look at the picture here, you'll see sort of the nub of what we're talking about. Basically, it's like a starry image when you look down. So initially, you could apply some astrophysical techniques to measuring things. We've actually got a lot more sophisticated since. But this gives you the nub of what's going on. You can see that how the light from Europe has developed over about 2 decades. There's been a big increase in the light level. So one thing we're studying, if we focus in on Ireland, is you get a number of interesting facts. One is the increase in light output with GDP, basically, with the economy. So it's a good proxy for how well the economy is doing because you've got money to burn, literally. It's also related to the population levels as well. So we have net immigration and a good economy, so light levels gone up. As a comparison, Northern Ireland is more or less flatlined, unfortunately. But there's about a factor of 10 then difference in how much light there has been developing over time. And this then is of interest. It's a good proxy. You can actually see where activity occurs. For instance, when you look at a satellite image during the daytime, it's hard to see what's going on. But at night, you can tell the difference between an area where you've had these ghost estates and one where people are actually living. It pops out straight away. You can see an image here, Dublin as well, giving you an indication of just how concentrated the light is, particularly around the center city where the university is. And then you can do statistics and actually look at the breakdown of light production. This is something we're doing for the Sustainable Energy Authority of Ireland currently. So what we can use is use satellite data. This is a space station image taken with a regular digital camera. Luckily, Commander Hatfield's daughter was at Trinity, so anytime he passed over, he liked to take a picture. And because it's so bright, it's easy to take a short exposure. So the original image, we see detail down to around the 10, 15 meter level. So we can see the little light pools around each individual light. And I have the council database. I can marry that up with the installed wattage or lumens, the amount of light produced. So we get data down to tens of kilometers. We can also request data that the astronauts take pictures. Hopefully we get something with a steady hand. And then we can compare with the known light sources and calibrate. And I don't have a picture, but it works out quite well at these low intensity levels because of the quality of the detectors. As I talked to some of you last year, quite linear low light levels. So we can actually measure the light and we can assign the energy produced by that lamp standard. Right? So things that are developing out of this, and big concern is, well, you know, how accurate is this when you're looking at a city? Because of course we've got tall buildings, we've got trees, and so on. So one thing we want to do is a bit of radiative transfer, modeling that, and as I say, do the breakdown and study it in more detail. And the structure of the city, we can do that with wavelet processes or Haar transforms and actually compare what's going on in detail, at much finer detail than we are doing currently. Okay, thank you.
Okay, so I haven't seen most of you before because I'm 900 meters off campus down here in the Advanced Microscopy Lab. This is Ireland's premier facility for electron and ion beams. And with one hat on tonight, I'm advertising 6 PhDs that need fully funded PhDs that need filling next year across this whole range of equipment. My group is based down there, and what we do is we look at the microscopes that these other guys use. And we say, well, if they want to take better pictures a decade from now, we need to start making these microscopes better now. So this is a typical transmission electron microscope. Inside it has a source, lenses, and detectors, much the same as you'd be used to. The best machine we have down the road cost about 5 million euros, so it's not practical to keep throwing more and more money just so every group can have their own microscope. We look at making these existing systems better, trying to reduce the cost. That's good for spreading the technology to small countries, developing countries, and also because we just simply can't afford 5 million every year. So right now, you take a lump of silicon in your hand, you can hold it, might look that. If you magnify it 20 million times, we already have the equipment to see individual atoms. That's an experimental image of a single crystal of silicon, but it's quite expensive to take such an image and it's quite challenging. We want to reduce the electron budget, so you damage your materials less, and also the cash budget. Okay? In the group right now, we have PhD students looking at electron emitters, objective lenses, and amplifiers, these green parts of the microscope. There are open projects that we can discuss in electron detector designs, adaptive apertures, something called adaptive optics, for blank technology, machine learning, if people are interested in that, and sample holders and design. This would ideally suit anyone across physics. I'm myself a materials scientist, so it doesn't have to be a particular flavor of physicist. An ideal person would be interested in both programming, optics, hands-on, building circuit boards, Raspberry Pis, 3D printing, all these sort of practical techniques because we want to end up building stuff. Okay? I'm only limited for time, so I talk about one of these topics. And also thermal management to actually reduce the greenhouse gases because these run 24 hours a day. Right, so that's a conventional detector, and that would take an image something like that of a sort of silicon transistor, but there's a lot of information that we're throwing away with current technology. A better detector that's in sort of quadrants, and the student on this project would be expected to visit experts in, say, Sweden and Germany to learn what they're doing. You can actually see the electric field within these crystals down to extreme resolutions. You can use that to look at dopant profiles, or in this case, using that sort of technology, the electric field around individual columns of atoms. Okay? The same technology can get you the magnetic field across domains. That's the images they are today. This is recent stuff looking at magnetic skyrmions. And in principle, that can also be done down to the atomic scale. So if you're interested in looking at the atomic scale, electric fields, magnetic fields, the things that build up matter, but also then sharing that technology for everyone else to have better pictures, this is what you want to be doing. I'll be upstairs all afternoon. Thank you.
You're next. There's one video there. I don't know if it's going to work. Igor, you have 3 minutes, okay?
Good afternoon. I'm Igor Spets. I'm head of the Applied Physics Group. So it's a large research group. We are well established. So throughout 30 years of my stay at PhD, I had maybe 50 PhD students finished, 50 PhDs and masters. Many of them are professors or having successful careers in their own right. So we also started 3 spin-out companies, so it's a mistake. There are 3. So that's a snapshot a couple of years ago. as the group is sizable, there's a range of projects, but they're all related to constructing materials on a scale of 1 to 2 atoms, big in some cases, films, analyzing the properties of these materials and changing the properties by changing the dimensions of these materials. So this is I just pick up a couple of examples. So this is the work on STM studies of the defects on copper. So this is sulfur, and this is hydrogen. So you can see that these are mobile defects on the surface of copper, and these are the electron waves generated by electropositive and electronegative defects. So these are the standing electron waves. So we do density functional theory calculations with David's group, in collaboration with David's group. We also engage in some high-resolution microscopy studies, electron microscopy. So this is the interface of do different oxides, but we also construct the oxides layer by layer down to a thickness of a couple of nanometers and show that you can engineer new materials in this way. So if you have interest, you can talk to me.
Thank you.
So I'm not Professor Sanvito, so unfortunately he couldn't be here today, so I'm here in his place. So the group started off in computational spintronics, but recently over the past few years we've kind of transitioned to a machine learning group. So, yeah, we're good with computers. So the idea with machine learning is you're using algorithms like neural networks to find correlations in data. So this is the same sort of technology that's used in things like self-driving cars, so it's very topical at the moment. So specifically, the project that I'm here to advertise is using generative models. So the idea is you have some data set. So this could be, in physics, it would be like molecules or materials with some property. And the idea is we'd like to make more of this data set. So maybe we have like superconductors and we'd like to discover new superconductors. So one way of doing this is to use what's called a GAN, a generative adversarial network. So here we have two neural networks. One of them is the generator, and it's trying to make new structures. And then you have a discriminator, and that's like a detective. It's looking at the fake structures and the real structures, and it's trying to tell which is which. So these two play a game against each other. And then hopefully, if all goes well, your generator can make new samples that have the same kind of properties as your distribution. So this is already being used to find new drugs, for example. And specifically, the two applications, or the two projects. So one is to use find new materials. So again, like this would be like superconductors or ferromagnets. And then the other idea is for many-body models. So you might be doing thermal averaging, so working out statistics, and that can be computationally quite intensive. So what we could do is make a small data set and then use GANs to make the population bigger, and then you get more robust statistics. So if any of this sounds interesting, feel free to talk to me later.
Thank you.
Professor Honjo, John is not here. He asked me to kindly show you his slides. I couldn't possibly comment or make any comments about the slide. He never gave me any sort of information besides just slides. So because this is being recorded as we speak, and this is going to everyone, as you know, many of your colleagues are abroad at the moment. So this is being recorded. So I'm just giving them the opportunity to have a look at the slides as well. Okay. In fact, this recording will be made available soon after this, most likely tomorrow. So in case you you fell asleep halfway through. I don't know, and you want to remember what exactly happened, you can go back and see the slides. So these are the only 2 slides that Anjo sent me. Okay, now, so this brings us to the end of this session where we show you the project. Now, the most important part is we go upstairs, right, and we have the chance to talk. But it's important to emphasize this. Don't be shy. Don't be shy. If you feel like talking to us and discuss about something, by all means, do that. Okay? Ask us questions. Is that okay? So we'll be upstairs with drinks, soft drinks, right? Tea and coffee, right? And plenty of time to talk. So see you upstairs. And can I just take the opportunity to thank all the speakers? So you could just thank all the speakers.